Welcome back. This is the final class in our mini course, and we will get to the end of our proof. Well, in particular, this result giving an exponential improvement on multicolor Ramsey numbers, particularly focusing on the 3-color case, because it's slightly simplified things to fix the number of colors. And so let's just take a moment to remember what we're doing. So to prove an upper bound on a Ramsey number problem, you have to say in any coloring on this number of vertices, you can find this monochromatic clique K vertices. So for 3 colors, we're saying, well, I think we use this notation. We could say RKKK or R3 of K is at most. So the, Edge-Separish upper bound would be like a binomial thing, which is basically 3 to the 3K. And we can do better than 3 to the 3K by some tiny but exponential improvements. It's the same we gave. And what we managed to do in the second class was we said we can actually reduce this to a certain statement. That was the first class of this part of the proof. I guess it's lecture 3 in the whole list. We reduced this problem to the so-called book theorem. So I'll write up the book theorem again, because that's obviously what we need to prove today to make sure we've got to the end of the proof. But the idea was that in order to find a clique of size K, of course, it suffices to find in one color a large book. What does that mean? For some T, you'll find a clique in one color of size T, and you'll find a large set which just joins to the clique all in that same color, and where this here is at least the Ramsey number KK, K minus T, and that's enough. The difference with the book theorem is we also said, well, we did a few reductions. We could reduce to the case that the graph was close to regular in each of the colors, meaning all the colors or the sort of color degrees were close to n over 3. And okay, we were looking at a multipartite setting where we'd already decided which vertices would play the role of x and the y1, y2, y3. But I mean, yeah, in a second I'll write up the book theorem and we can look at it in detail. And we'll also write up the algorithm. Well, it's good to just say completely informally maybe what the algorithm is, because once you put all the details up, then your brain looks at the details, right? So it's good to just say, without too many details, what's our plan to find one of these? We'll always have X, which is sort of the set of candidate vertices to become part of the book in the future. And we're going to sort of simultaneously have 3 attempts. We're going to build a set T1, which is a clique, just join to Y1, all in the same color, maybe red. We'll call it 1, I guess. We'll have another T2, just joined, of course, just to same color as a clique again, and just join to Y2, color 2, and you can have a third one as well. So the algorithm does this, and of course it's trying to do it in such a way that you definitely do enough steps. You want to do at least T steps in one of the cliques, because you want to find this structure. Well, I mean, a priori you can do this for any T. It happens that it's just useful to fix a value of T. In fact, it will be K over 2 to the 30, and we'll prove it for this T. In fact, right at the end of the class, after we've completed the proof, we can have a little discussion of some of the choices of constants. Because we're doing the 3-color case, I can just make up, this constant would work. But you may feel it's not completely satisfactory that I just tell you, look, let's choose these constants, do the proof. Ah, that's the answer, it worked. You may think, well, why did you decide that this was 2 to the 30? Right? So the little discussion we have after the proof hopefully will explain where these choices come from. So, yeah, the idea is you want the process to go on long enough that one of these cliques gets to size t, and we're going to need to make sure that the corresponding set on the other side stays larger. So the two main challenges today are really, we want to understand, understand, not understand. It's understanding something to fall over us. To understand evolution through the process of the size of x, I guess you could index the time by s, and understand the evolution of each of these y. So these are like the two big things we need to do. If you understand the evolution of x, you can say the process lasts long enough in order that one of these gets to size t. And if you understand the evolution of these sets, then you know at the end of the process, it's big enough that you really have proof of the theorem. So, as I say, we can now write up the book theorem, which is our main objective, it's the thing we need to prove still. And we can write up the algorithm, which is sort of our method, our way we're going to try and prove this theorem. And then the rest of it will just come down to the analysis of understanding the evolution size of sets. In doing so, we'll also record a couple of facts from the last class, because there were some things about the number of boosts and the densities that will be useful as well. But anyway, let me write up the book theorem first, which is what we're trying to prove. Book theorem. So for some reason we fixed delta as 2 to the minus 40. We let x and y1, y2, y3 be 3 sets. We may as well make it disjoint. I think you don't need disjoint for this argument. The paper no, we don't have disjoint. It's just kind of easy to think about. Disjoint with size, with cardinality, each with cardinality, at least. So it's going to be nearly this 3 to the 3k. It's going to be smaller just by an exponential factor. And I think we put k over 2 to the 66. So you need a little bit less than 3 to 3k. And let them, I'll just say let them be 3 colored, because I don't want to write too much. What do I mean? You want to color all of the pairs in the union of these sets. Right, so you have these 4 sets, take the union. I say let them be 3 colored. I mean, you color all the edges, the pairs. Take that. Then, the conclusion is, sorry, one more thing. Of course, we can include the minimum degree condition because that was part of the reduction to book theorem. They're 3 colored such that for all I, 1, 2, 3, and for all x in x, everyone in x has good degree in color I to the corresponding y I. So the number of neighbors in color I of x intersect yi is at least a third minus delta times the size of y. Okay, now, then there exists a monochromatic TM book, and here it doesn't really matter what T is, but T will happen to be K over 2 to the 30, and M is at least R, K, K, K minus. Okay. So that's the theorem we still need to prove in order to deduce the Ramsey upper bound. It's a very similar statement, right? It's just saying the observation that suffices to find the book. And because we did those reductions, I guess officially it's in lecture 3 in this series, the first lecture on this proof, we did those reductions so that we could really already have this structure and already have this minimum degree condition. Now, once you fix that this is your objective, you have to think, well, how do we do this? How do we find these books? And it's exactly as we said here in the sketch. We have an algorithm. So we'll call it the books algorithm. So you start with, now when I write x of something, this means the time from the point of view of the algorithm. We did this in the last class as well, right? After s steps, then you had minimum degree condition like pi of s. So that's what this means here. So this means at the start of time, we set x equal to our x from here. Each of the yi's is equal to the yi from the book theorem. What else do we have? Ti's are empty to begin with. Anything else? Well, I guess pi of 0 is the corresponding density. Actually, observe all the pi of zeros are at least the third minus delta. Yes. Actually, one of the things we proved in the last class is all the pi of s are always at least the third minus 2 delta throughout the process. Maybe it's worth remembering as well, we'd be using, we would stop when, maybe let's put this right to the bottom. We stop at a stopping time tau, which is if either x gets too small, it was like e to the 2 to the 25 or something, or one of the books gets to size t. So or there exists I, ti has size t. Right, so let's remember what the possible steps are in the algorithm. So I know it's confusing. I'm going to do 1, 2, 3, but the algorithm is such that every time you do a step, you do 1, and then you do either 2 or 3. So what's the first thing you do is you apply the key lemma with all these sets, and you have to choose the alpha, right? The alpha I, I'll call it alpha I of s minus 1 because it's going to be a function of situation of time s minus 1. So I'm going to describe the step which takes you from s minus 1 to s. You know, just like an induction, you can do from s to s plus 1, or s minus 1. So we'll assume that you're looking at the situation you had at time s minus 1. What do you do to choose the alpha? You look at your surplus in this degree, minimum degree condition, above a third minus 2 delta, and then you divide all of that by t. Then that's the amount you're willing to lose. Now, we're kind of making this promise. If we're going to do a color step, we're willing to lose little in the minimum degree condition, but not too much. And in the boost step, you win something corresponding. Okay, so depending on what you get out of the key lemma, I mean, in a way, I don't want to recap everything about the key lemma. And I think the last time we mentioned the book's algorithm, we just said, what does it do and what information do we need? So let's just do the same again. So either you do the color step, which is super certain if you have the first outcome of the key lemma, and then you're basically updating XS becomes like the x primed, which is basically the neighborhood in color I, some vertex x, intersect x. Y, I of s, one of the yi's is updated to be the what's contained in, I guess, the neighborhood in color I, intersect yi, and x joins ti for tis. Now this x in yi here minus y minus 1. Not much space. Anyway, you add x to. So in this picture, this is obvious, right? The color step is you find someone and his red neighborhood on this side and this side are good, in the sense that the minimum degree is only going to go down by most alpha. And then you add this vertex to T1, in this case from Ti, and you restrict x to this set, restrict y1 to that set. So a color step is like that, could be in any of the three colors, but it's like that. And if you don't do that, you do a boost step, and that's when you found some large lambda. For us, it's lambda at least 2 to the 42 or something. And you go into subsets in x and y. And the important thing here is you increase the minimum degree condition between xs and ys is bigger than the one you had before. And what did you add? What's the new extra? You add lambda times that alpha I of s plus 1. I tried to write it in too little space, really. I mean, I'm going to have to mention some other facts as well. So maybe what I'll do is the book theorem. We can kind of just remember this first part. It's not much information here, right? We kind of just want to know what we need to prove. We just need to find this book. Maybe actually the book theorem is clear enough, right? Maybe I could write a super short version. Okay, so let's write a super short version because we have limited board space. So we need to. So the cardinalities of each of these sets is at least 3 to the 3k e to the minus k over 2 to the 26. I think we can remember we start with the minimum degree condition, third minus delta, right? Or maybe for all x, n, I, x, and so y, I, at least third minus delta times the size yi. Then there exists monochromatic Tm book. And okay, it happens to be that T is K over 2 to 30, and N of these Ramsey K. So, yeah, in a way, a lot of the properties about the evolution of the minimum degree are not so important to us now because we sort of covered that last time. Let's see what facts we do have. Well, one fact yeah, I suppose I did do this too small, and now it's kind of already written here. Yeah. Okay, I'll put just more information up here. So in the color step, if you remember, we were using CI when it was a color step in color I. So we're going to be interested particularly today in the size of the sets. So if you do a step in color I, then how much does X go down? It's actually at least, I'll call it epsilon xs minus 1. And this is where epsilon is e to the minus 2 to the 25. Okay, that's an important number. And that was just what came out of the key lemma. If you're going to do the color step, you know, keep at least this proportion of the set X. And in the boost step, if S is a boost step, how much does X go down? Then that's where you get e to the minus 12 root lambda minus 12, where the lambda depends on the step. E to the minus 12 root lambda S minus 12. So that's the information, particularly about the size of X, which is what we're going to be analysing first. It's also useful to have, so in the boost steps, you're going down like this. So it's good to have some control of, here as well I have X. It's good to have some control of the sum of the square root lambda S. This was one of the lemmas from last time. So let's remember that it was called lemma 2 last time. Lemma 2, the sum, in fact, what I'm going to write here is implied by lemma 2. If you do the sum of the square root of the lambda j's over j a boost in, if you did it in one colour, which is what we did last time, we had a bound which was like 2 to the minus 19 t log 1 over delta plus some other term which had a root t. Okay. Now, if t is large enough, which happens if k is large enough, this term is bigger than this term. So I could say 2 to the minus 18 and it's just this. Also, before I was saying over BI, there are 3 different colours in which you do boosts, and they all will decrease X at some point, right? So we actually want to bound over all boosts, doesn't matter which colour. So here I'll put 2 to the minus 16 t log 1 over delta. I think actually this bound is one of the bounds where it's actually much stronger than what we need. When we go and do the proof, this bit will win by so much, we'll say, well, that was a bit silly. But fine, we've got the bound. So some of the root lambda j's is not very large. There was another fact which will be useful. It's fact 3. It was just about not having too many boosts, right? And I think we had the size of BI was at most t log 1 over delta over 2 to the 40. It's fact 3 of the last class. Okay, so let's think about as we said, we have 2 main tasks to do to complete the proof. We need to understand how XS is evolving, and hopefully by doing so, we can say you really do get to a peak of size t. Don't just use up X and it's all over. And second, we'll come to the evolution of the YI. You need this to stay big enough that you win. So let's see how this works. Starting with our friend X. Understand. S, already a lower bound, this guy. Right. So what do we think? What would be just a good general lower bound on the situation? I mean, what we want, let's see what we want. We want at the end, we're going to stop if either X gets too small or we find what we want. So what we want is at the end, X is not too small. So we want X tau is at least e to the 2 to the 25. This happens to be our epsilon, right? Or 1 over epsilon. I don't know if this really doesn't really matter, but we can just say suppose not, right? Do a by contradiction, suppose not, suppose not, and then xt x tau is less than something minus one. And we can think about how it gets so small through the steps. What were the steps that happen to make it decrease? In other words, we could compare this to x0. X tau is at least, well, you've only done two types of steps that reduce the size of x. You've done the color steps, and then you go down by a factor of epsilon, this e to minus b to 25. So you've done this for all of the color steps, right? Now, how many color steps are there? So we're in this kind of, I suppose we're in the case where x ends up being too small. So it means you didn't get to complete your clique in any of the colors precisely. Right. So you only did like less than, was it 3t minus 3 or something? You know, color steps. So if you do more than that number of color steps, then one of the cliques is big enough. So I'll say you've done at most 3t, maybe 3t minus 1. Anyway, so you have this bound. You know, this is how much you've gone down at most in color steps. How much have you gone down in boost steps? Well, you go down by e to the minus 12 some of these guys. What I'll do is I'll just put e to the minus 16, and then we can ignore this other 12 because it gets absorbed. Just because it's easier to just have one term, right? Maybe I'll write x with minus 16, the sum of the square root lambda j. Or j in, this is only in the boosts. Times x0. Because we're counting all the ways, all the multiples x might have decreased since the start of the process until this point. You go down by epsilon in the color steps, but you had less than 3t of those. And you go down by e to the minus root lambda in the boost steps, 12 or 16, whatever. And so you have this. Now, because we've done a contradiction thing here, then we're really saying already, we already know this is small already, so we have this. And so it's going to turn into an upper bound on x0. So all we need to do is show that this upper bound on x0 is wrong. In other words, our original x is bigger than whatever, and then I'll give the contradiction. So therefore, x0, or in other words, the original x that we given in the book theorem, is at most. All right, work those epsilons the other side. Epsilon to the minus 3t. And this exponential of now it'll be 16 sum of the boost steps square root lambda j. Okay. But each of these two things is just something we can calculate, right? It's not that different. The epsilon was e to the minus 2 to 25. So epsilon to the minus, like an e to 2 to 25. So this first thing is e to 2 to 25 times 3t. And this second one is like plus 16 times, if you like 2 to the 4, whatever, times this upper bound, right? We have an upper bound of the sum of these guys. So well, it's going to be 16 times 2 to the minus 16. So like 2 to the minus 12 t log 1 over delta. It's worth noticing log 1 over delta is at most 32, 2 to the 5. This is just because delta is like 2 to the minus 40, so 1 over delta is 2 to the 40. Log of 2 to the 40 is less than 32. It's just a calculation. It doesn't, as I say, it doesn't really matter because this term is kind of going to be negligible. Because you can see what we have here. It's easier if I write x. This term is at most 2 to the 27 times t. And this term is like 2 to the minus 7 times t. As I said, the boost terms in this case are really not using up very much. But so now the numerics come into it, like t is 2 to the minus 30 times k. So this is less than e to the k. And e to the k is less than 3 to the 3k minus a bit, right? So that's the contradiction. Of course, there was no need to write this as a contradiction. You could just say the x0 is big and just directly calculate a lower bound for this and see that it's not too small. But it's the same thing, just written it as a contradiction. Okay. So the idea was, if you do end up being too small, then you can just think about what you lost in every step. And okay, we wrote it this way, and you introduced that the initial step really wasn't very big. And that's a contradiction because you know the size of the initial step. It's sort of interesting, in fact, this part of the argument isn't even super optimized. Because like, we only needed the original x to be size like e to the k, e to the k over 8 or whatever. Which is so you don't, the x doesn't actually need to be quite as big in this argument. So the version of the result written in the paper actually specifies how much you need in each side in the ways you don't need to put so much in the x. But given that you're just going to split into different sets, you kind of, from the point of view of the proof, you may as well make them all roughly the same size. Doesn't make much difference. So anyway, this is half what remained of the proof. We've done the part showing that x stays big enough, and so that you do go long enough to find this book with on one side a cleek size t. What you don't know still is whether on the other side you still have enough vertices to win. So perhaps we can go to that part now, which will be the understanding the y's. I guess I should get rid of all of this. Understanding y s. Well, and in particular, y at the end. We're probably still going to just use the same information. I think the other piece of information which will be very useful now, yeah, in a way, I mean, we've seen the book algorithm. We kind of know how it works. And for calculating the y, it's actually not quite so important. So maybe I'll get rid of that to have a bit more space, because we're going to need a bit more space. And there's another fact from last time, which is kind of clear from the rule and our choice of alpha, but we said it explicitly last time. The min degree condition between x and one of the yi's never goes too far below a third. So for all I in 1, 2, 3, for every step of the process, the min degree condition as PIS is always at least a third minus 2 delta. I'm just because it's useful to use exponentials. You can think of this as the third times, it'd be like 1 minus 6 delta or something, right? And then you can convince yourself, you can just put like e to the minus 8 delta or something. So this is at least the third times e to the minus 8 delta. It's just slightly more useful because all the calculations have these exponentials in. So we may as well have an exponential there as well. Right, so where are we with understanding the evolution of the y's? Understanding right, so I guess there's two things we want to say. So in one of the colors I, we do get to size t. And it's only that color we really care about. And I guess it works. The argument doesn't really care which color we're talking about. But it's only really for the one where the clique gets to size t that we care what happens. And so in a way you could say you have two challenges. One, you need to control how big this is. Well, the other side, I don't know, it's really a challenge, but we're going to compare this to the Ramsey number. So we should say something about how big this Ramsey number is. If this is our objective, if this is the thing we need to beat, we need to have an idea, well, how does this compare to all the other numbers around, right? So what's a good way to bound this? Well, the English-Seckeresh bound gives this kind of multinomial thing. And then you could just think about how do the multinomial terms evolve as you let this guy bend. So what you get is the following. So if I do... Right, so let's just start with an observation. If I do 3k, choose k, k. The third one is the thing I'm interested in varying over time. So I'll do minus s plus 1. Now, if I write that, that's what? 3k factorial over k factorial, k factorial, k minus s plus 1 factorial. Okay. And I want to compare this to one where I just have s, right? And I can put 3k factorial over k factorial, k minus s factorial. And so I'm not doing the wrong thing. I'm doing the wrong thing because I don't want 3k. This is also going to go down. Sorry, yeah. So it's 3k minus s plus 1. 3k minus s plus 1. Okay. So what I can say is I want to compare this to the one which is just with k minus s, and say what's the multiple. Well, in this one, you have an extra multiple on top, which I think is the term 3k minus s. Right? What am I saying? It's like... you know, I'm going to just check. Right, so if you think about it, there's a term which you would have as 3k minus s. Well, there's a term you would have here that you don't have here, which is the term for 3k minus s. So this one still has that thing making it bigger, so I guess I should put 3k minus s there. And at the bottom, this has a k minus s, this doesn't, so it's k minus s. So that's the ratio between like two consecutive ones. So if I think of this ratio equals k minus s over 3k minus s. We want to think of this as being close to a third. Okay? And this is related to the fact if you just do steps in the end of separate algorithm, you're probably going into neighborhoods of size about a third. In our PUC algorithm, this is going down by a factor of about 3 every time. A little bit less than 3, a little bit less. And the fact is this ratio is a little bit less than 3. And that's exactly what we need. If this was always exactly a third, then we would be losing. This is a little bit less than. And you could do that by thinking of this as a third, and then you could just like multiply on top by 3, right? You'd have 3k minus 3s. So the part which is 3k minus s would give you 1, right? And then you have minus 2s over 3k minus s. I think, yeah, one way to do it, which I've got here, is on top, if we divide by k both, on top, what you have is 1 minus s over k. And here, if we take out the 3, and we divide by k, you have 1 minus s over 3k. And let's think about this here. This is like, you could think of this as 1 minus s over 3k minus 2s over 3k. Because then this is just s over k, it's 2s over 3k. Then you could just write this as 1 minus this bit over this bit. But then you just use the denominator is less than 1. So in particular, this is less than or equal to a third minus 2s over 3k. Sorry, 1 minus, yeah. Anyway, it's just easy algebra. In other words, the ratio relating this to the previous one is a little bit less than a third, and in a way we can count sensibly. And now that will allow us to think about this, which is basically doing this a bunch of times, because this implies, so now r k minus t is less than or equal to okay, 3k minus t, choose k t minus t. And this you can basically just apply a product of these ratios to go from the diagonal case, we're going to compare it to 3k, choose k, and think of just doing these steps lots of times. And so getting the product from s equals 0 up to t minus 1 of, well, this, I guess, but we can use that to most. That, so it's most. This product, the third happens every time. So it's 3 to the minus t, and then the product of this bit. Maybe we'll also use 1 minus x is a most e to the minus x, right? So it'll be a product of. I can do quite a few steps here, because now I've got a product with an exponential. Of course, I'm going to just turn it into exponential sum. It's all very elementary, right? But it's sum 2s over 3k. Now, if you sum from 0 up to t minus 1, basically you've got a factor, and then you're just summing the integers from 0 to t minus 1. So it gives you t minus 1 over 2. 2's cancel. So we've got 3 to the minus t exponential of minus 2's cancel t minus 1 over 3k. And what we're going to use, so maybe I'll just put it here like it's a lemma. Call it lemma 3, because we've already got lemma 2 on the board, is this the result. Sorry, this is always a multiple of times 3k choose k. And this is times 3k choose k. Of course, 3k choose k is at most 3 to the 3k. So it's at most 3 to the 3k. And what we've proved is the following lemma: r k minus t to most 3. We've got a 3k minus t. And we have an extra factor. And I'm saying it's this extra factor which is sort of allowing us to win. It's the reason why doing a book is useful. Because if you were doing a book and you were just getting a third every time, and somehow this inequality went the other way or something, it would all be a waste of time. But you've sort of won this. And what I'll say is you've won e to the minus t squared over 4k. So I know here you have t minus 1 over 3. Let's just call that t. This is at least t squared over 4. So this is our upper bound of the Ramsey number. And in a way, I'm saying, I know it's just details, it's just multinomial things. But in a way, this was very useful because it defines our objective here a bit more clearly. Rather than being an objective in terms of a Ramsey number, who knows what the value is, it's an explicit objective. We just need to show the book is at least this big. Or the other side of the book is at least this big. If it's at least this big, then it's at least the Ramsey. So let's say we want, so let I be the I such that your clique part, Ti, does get up to size T. So I guess it's Ti of tau, because that was the stopping time. What we want, all that remains to prove the whole theorem, or say want, all that remains to prove the whole theorem, the book theorem, and therefore the whole theorem, is the following. At that same time, the other side of the book is at least this value, 3 to the 3k minus t, e to the minus t squared over 4. It's good to have a clear objective. I mean, you still have to actually do the thing, but at least we know what it is we should do. So what do we think we can say about this guy? Now, yi tau is at least, what do we know? How does this go down and when does it go down? It goes down if you do any type of step in color I. When you do a color step in color I, then it does involve going to I neighborhood inside here. And you exactly lose a factor of pi of that s, that time. But these are all at least a third, well, times this factor. So we have at least a third e to the minus 8 delta for every color step in color I. Also for the boost steps, it's the same thing. Because in the boost steps, you may go much more in X. There was this root lambda stuff, e to the minus 12 root lambda. But on the other side, the set we picked was the neighborhood. Maybe the n prime, but anyway. It has still size pi of s, pi of s minus 1. So it has the same inequality. So actually, you're losing the same in the boost steps in color I and the color steps in color. And of course, we multiply by the original. And we'll just put what? yi or y of 0, the original subway. It can't be that complicated, right? This term is reasonable. We've already seen things about these numbers. We know how many vertices we have originally. This cannot be a difficult calculation. Okay, a few terms appear, but it's basically fine. So, what we have, okay, let's just put, just to take it slowly, I'll just put the same expression here, and we can think about these two. How many color steps do we have? Well, in each color step in color I, you put something in the clique, and in total we put t things in the clique. So in fact, we know this is exactly t. And how many boost steps are there in color I? Fact 3 tells us not too many. So now we have plus t log 1 over delta. Maybe we can just use, let's use here the fact. Our delta is such that log 1 over delta is the most 2 to the 5, we said. So let's just put this immediately as the most t over 2 to the 35. So all we have here is the number of boost steps is the most t over 2 to the 35. Let's put in the, we won't do contradiction this time, let's just put in the size of y0. So this is 3 to the 3k, e to the minus, was it k over 2 to the 66? Good. So what have we got? So actually, even though I put this just as one term and these two different contributions to power, we'll actually kind of deal with t of these in one way. We'll deal with these in a slightly different way. So for the t, they're going to produce a 3 to the minus t. So we just put that on the 3 to the 3k minus t. They're going to produce an e to the minus, I guess I could just do this x thing. We're going to have minus 8 delta t. Maybe we'll put that guy on the end. These other guys, I don't actually need to be quite so precise. I'm just going to use that this expression in here is at least e to the minus 2. Okay. It's a bit less than the third, so it's less than it's bigger than e to the minus 2. So I can put minus 2, so it's going to be minus t over 2 to the 34. And here is the minus k over 2 to the 66. And all we really need, look, left-hand side of the board, right-hand side of the board, we just want this to be bigger than this. We've actually chosen our t is going to be k over 2 to the 30. So this is really 3 to the 3k minus t, if you like, x minus, what is it, k over, we've got 2 to the 30, we've got a 4, so this is squared. So here's 2 to the 62. So we just want to be bigger than this. This bit, as I said, we're going to come back in a second and kind of explain why the proof works. Because what's going to happen in the next minute is I'm just going to say these are all smaller, so we win. And it's a little bit, might not be very satisfying. But as I say, we'll come back in a minute and explain it better. But remember, delta's 2 to the minus 40, t has a 2 to the minus 30. So that's like 2 to the minus 70. So you're going to get 2 to the minus 67 times k. T has a 2 to the minus 30. So this is 2 to the minus 64 times k. And this is 2 to the minus 66 times k. And all of that is less than 2 to the minus 62 times k. So you win. So this is at least this expression you need. Okay, as I say, in one sense, it's a bit of a disappointing answer because all these constants or these choices of delta and t were given to us, and we just went through the calculation and it worked. So it may have a bit of sense. I don't see why that worked, but at least we did get to the end of the proof. We've completed the proof that of the book theorems, you do get a large enough book by applying this algorithm, and that does imply the main theorem. So it's pretty good, pretty good. So, yeah, we could just stop for a minute and we can go back and I'll think if it's possible to kind of explain why this proof feels like it should work. Because that's sort of more useful, maybe. I thought it was kind of cool that in, like 4 classes, towards this part of the course, you can do the full proof, basically all the details, and it really works. And it's not too heavy, right? Some details, but it's basically possible to do the whole thing. So I thought that was kind of cool. But yeah, the way I've done it, when you actually go and do all the details, your life becomes easier by saying, let's fix this value, let's fix this value. And the more you do that, maybe you have less power to explain why these are the right choices or where these choices come from. Inside it, there was sort of some optimization, or there was some playing off the parameters against each other. So let's try and discuss that to try and see why it was clear the proof should work. So we kind of, in some senses at the end, right, we've completed the proof of the book theorem, that completes the proof of the main theorem on the exponential improvement. But you may still be sitting there thinking, okay, it's true, but do I really feel it's true? So let's go back and have a bit of a discussion of how the parameters relate to each other. We can see the trade-offs do seem to work, and so it should be kind of natural that the proof works, in a way. So maybe I'll get rid of this part here again. And then we can see why it was natural, in a way, the proof should work. And really, it's funny, there's sort of 3 inequalities that matter in all of this. And I should say there's sort of 3 parameters that matter in all of this. The 3 parameters are delta. You have to choose so delta, in a way, has 2 different roles, but they're kind of similar. One is how much density you're willing to lose, measured by delta. And in a way, it's the same thing, right? But it's also the density condition you have at start. But they're pretty similar things. It's all to do with what do you want to know about density condition. So you can imagine, I mean, just to think about playing these things off, if you choose a very small delta, you're asking for a much stronger condition initially. Well, maybe in other ways that makes it more difficult to win, because maybe it's even more difficult to get into this situation. So, if delta gets too big, then what we have here a term with the delta t in that, and if you let delta get too big, then it means you're going downward too much. So maybe that's quite clear. Okay. The other important parameter is sort of t. Or you can think of it as t over k. It's like, how big do you want this clique to be in one side of the book? And of course, it's going to be some function of k. If we want to get an exponential improvement, t is going to have to be something times k. And in this case, we took this to be like 2 to the minus 30, right? The third one is a very important parameter, which I was a bit rude. I didn't even give it a name. Okay. For us, it was 2 to the 42. What was 2 to the 42? It was an important number for us because it was when we chose if we were going to do a boost step. We had the geometric ladder, and it was all about, you might get a cap, you might get sort of lots of things bunching up, and then you could use that to get the key lemma and all the stuff, and you could choose where you count as saying it's like a big cap, a big distortion. And we just chose this number. Right? But it could have been, you could have chosen a bigger number, you could have chosen a smaller number. It was a choice for parameter. So let's call that lambda 0. So maybe I could put these three things here. I'll put in brackets the choice we made, which is not at all saying it's the correct choice, but it's just like one way to do the choices that works. And this one was 2 to the minus 30. And the idea is we can think of the places where there was a dependence between these parameters, and what did we need to do? What was sort of necessary for the proof to work? So and it all really comes down to the things we've seen today. What did we need today? So for x, the size of x, we needed something like epsilon to the minus 3t. We didn't want this to be too big. I mean, the thing we used was like less than e to the k. You actually have a bit more room here, because this could be as much as nearly 3 to the 3. But basically, I'll just put this condition. This is what we have. So this is a condition on epsilon. But epsilon isn't one of our key parameters here. But actually, it's related to lambda 0. So where did the epsilon come from? We said in the key lemma, you either get a color step or a boost step, and you get a boost step if your lambda is at least lambda 0. But what if your lambda is just a tiny bit less than lambda 0? Then you still have to do a color step. And remember, the cost of that color step will be like e to the minus root lambda for this lambda. So it's basically like e to the minus 12 root lambda. So because our lambda was e to the 42, this was 2 to the 42, this was 2 to the 21, and then you turn this into e to the minus 2 to the 25. This is where the epsilon came. But in general, the epsilon might be whatever it's e to the minus 2 to the 4 times root lambda 0. That's kind of what the epsilon really is. So if you put that information in here, and I guess you take logs on both sides, okay, then you're really saying, was it 3 times 2 to the 4 times t times root lambda 0 should be less than k. In other words, let's just simplify this. It's sufficient to be sufficient. I'll just turn this into 2 to the 6, whatever it says, sufficient. This 2 to the 6. But that's like our first condition you might want to satisfy. This relates the different parameters. There is a second condition to do with x, and it's to do with the boost steps. Well, I think I won't write it out, because it turns out that from the point of view of x, the boost steps, they don't hurt you too much. That's what we saw anyway when we did the calculation with x. The contribution of the boost steps was much smaller. And that kind of is the case, right? But officially, you could do a condition for that. Right, so what are the conditions we came to for the size of y? Well, there are lots of things that were kind of removing or making our bound smaller. And we want them all to lose to this term here, right? So what do we want? We want one of the terms we lost was this 8 delta t. It was to do with the density being a bit less than a third. And so maybe I'm going to say I want this to be less than t squared over 16k, just because there's going to be a few terms to sum up. We want them all to sum up to less than t squared over 4k. Again, these powers of 2, they don't really matter very much. I mean, they're just constants, and there'll be some constants around you need to keep constants. In a sense, they don't matter too much, because when we go on to the R color version, this generalizes to R colors for any R. And then instead of being constants, there'll be functions of R. Maybe if it's 10 colors, you know, these are much larger numbers. But basically, as we'll see in a minute, there's still a way to optimize correctly. Or optimize or choose the parameters so that you get some way. Right, so that's another thing we want. And this is going to, if I move one t over there and cancel, this is something more like, because this is t less than something's okay, this will be like t more than, t greater than, whatever it's 128 delta k. So this is a second thing we want to satisfy. And let's get another one. This is also for y, but to do with the boost steps. We said we were going to lose like most e to the minus 2 in all the boost steps. Right? So we kind of had an e to the minus 2 times the boost steps. And we also want this to be, we want twice the number of boosts to be less than t squared over 4k. So, I mean, you don't need to lose quite as much as that. So we'll just say we want the number of boosts to be less than t squared over 8k. So if we want this to happen, we need to remember what was our bound on the number of boosts. Our bound on the number of boosts has this weird 2 to the 40 here. Surprise, surprise, that 2 to the 40 is related to lambda 0. Why? Because if you, well, I mean, it's a bit of a detail, right? But we have this expression for how much you go up when you do the boost steps. It's 1 plus lambda over t. And the way, so if you want to bound the number of boosts, obviously you have more boosts if you do smaller boosts. Then the smallest value of the boost you consider would be lambda 0. And so really, this is really like 4t over lambda 0. That's what's happening with this fact, if you prove it in the general case. So the upper bound you have for the number of boosts is really like you want 4t log 1 over delta over lambda 0 is most number of boosts. You want this to be a most t squared over k. Again, we can cancel a factor of t. Again, it's going to give a bound like t is bigger than. This time, It's, what is it, 32 log 1 over delta over lambda 0 times k. So, yeah, each of these things is a little bit of work, but you can work out the necessary dependence you need between the different parameters. And now let's simplify by putting these three things together in one line and see how we could pick the parameters correctly. I think I'll do it based actually on, I could say t over k, but I think I'll do k over t just to switch around. So k over t, this first one is saying k over t is at least, okay, 2 to the 6 root lambda 0. So 2 to the 6 root lambda 0 is less than or equal to k over t by 1. For 2, you want k over t is less than, was it 2 to the 7 over delta. And this one is in k over t is less than 32 log 1 over delta. No, sorry, the dog on the other side. Sorry, yeah. Lambda's k over t less than lambda 0 over 32 log 1 over delta. Okay. Now you can easily see a condition which is forced on you, which is a certain low amount of lambda 0. Because here you have a multiple of root lambda 0, here you have lambda 0 over something. So it tells you something like root lambda 0 is at least, then you're going to get what, like 2 to the 11 times log 1 over delta. So it's already saying your lambda 0 is going to have to be quite big. Seems like 2 to the 32. We did 2 to the 42. This is saying it has to be at least 2 to the 32. And one thing that tells you immediately, I think, well, for various reasons, but this is one of them, this proof is not going to give you really good quantitative improvements on it gave you the exponential improvement. It's good news. We like exponential improvements. But if you really, really care about, what's the constant, it's probably not going to go so far the standard. Because, this is forcing the lambda 0 to be pretty big. And then that feeds into all sorts of things like the epsilon. And then it means every single step you're going to be going down like e to the 2 to the something. I'm just saying it doesn't seem super efficient. But anyway, you can see from here, you can choose lambda 0 large, so that at least these two work together and say the sum interval looks possible. And then you basically just need to choose delta small enough that this is also bigger, right? To make sure you have some space. Okay, there's some slight interference because here you have a log 1 over delta, but obviously, like if you make delta small, this goes up way faster than a log, so this relation doesn't really cause you any trouble. So in other words, this gets big much faster than this is making this term smaller. So that relation between a delta and a log 1 of delta is not a problem. Another thing this kind of makes clear is when we had the geometric lever, we had this tail behavior, and we managed to get the tail probability behaving like e to the minus root lambda. You really would want, you do need that to be like a sub-exponential. If you just had a property like e to the minus lambda with even a small constant or something, well, maybe, you'd definitely be in a difficult situation because you'd have two terms of the same order here, right? Maybe if the constant was small enough for some reason. But anyway, it was very, important that you had a good control of the tail, and it being e to the minus root lambda was, in a sense, easily sufficient, because this function is then growing more slowly than that one there. Yeah, and I think even though this is just details and saying how we choose the parameters, I think having seen it this way, it can make you feel a little more confident that the approach does carry over to more colours. Right? I mean, obviously the sketch just stays the same. This book algorithm I could easily do with 10 colours instead of 3 colours, and you basically don't need to change a word, because everything just says for some I do this. But I think this type of thing, it maybe help reinforce the feeling that it should be possible to choose the parameters correctly so you get some group as well. Because even if this was a function of R, and this was a function of R, this was a function of R, well, you take lambda 0 too big, bigger than some other function of R, and then you get a nice interval between these, and then you take delta small enough, you know, it feels pretty convincing that you can always deal with this independent of what these 3 numbers are. So I hope that gives you an idea of, you know, what happens in this particular proof. There's a whole world out there of problems in Ramsey theory to think about for anyone else who's interested. Even on these problems, the gap obviously stays, it remains very, very large between the lower bounds and the upper bounds we have. I mean, it's a few years ago now, but I still recommend, of course, to anyone the survey of Conlon, Fox, and Sudakov and Ramsey theory is a good overview of what's going on. There's lots of nice problems we've seen in parsing, like multiplicity problems, K4 multiplicity. There's problems you can do where you do multicolor Ramsey, but you just say, I want to find a triangle in any color, where you have the set of colors grow instead of the size of the thing you're looking for. So I do encourage you to, you know, read around the subject as well. We can't do even, you know, 10% of what we'd like to do in a mini course, but there's a whole lot of nice things out there. So that's another recommendation for the holidays. Okay, so cheers everyone. Let's end it there.